Hello, welcome everybody. Can you hear me okay? Yeah? Good. Welcome to some mathematical circus. I will be your ringmaster this afternoon. My name is John the Juggler. You can tell that I'm a ringmaster because of the black and white outfit and because of this very large curly mustache I have. Of course, no one really has a giant curly mustache like this. I'm just kidding. It's fake. Okay. So now let's get serious for a minute about juggling, because you may not have known, but there's a lot of math going into the discussions of juggling between high-level jugglers. I'm going to tell you a little bit about that, but let me get loose. I want to move around a little bit, and I'm going to show you some juggling as we talk. So, on a more serious note, everyone has their own personal philosophy about juggling, as do I. I've developed mine over the years doing many juggling acts. My philosophy of juggling is that it doesn't matter how many. Okay? So all of you can start with a one-ball juggle and consider yourself a juggler already. Now, one tip here while we're going is that if you want to try out some of the juggling things with me, you can grab some juggling balls you might have laying around the house. Of course, I realize not all of you may have juggling balls laying around the house. One suggestion is to take a few socks, kind of roll the socks and tuck them up into it themselves. And you can use 3 socks as juggling balls pretty well. So give it a shot and see if you can figure out a few things. And join me afterwards. We can talk about how to learn how to juggle. Okay. So I can throw a second ball into the juggling pattern. And now I have a 2-ball juggling pattern. An expert juggler could even look away as they juggle this pattern. Just imagine how entertaining that would be. Okay. Now I'm going to seamlessly add a 3rd ball into the 2-ball juggling pattern. Okay. Here's the 3rd ball. I'm going to insert it into the pattern. Somewhere in the pattern, if I just put it, pattern somewhere. Add it there or put it here. Oh, that works out pretty well. Okay, let's start here. All right. So we've arrived at the most basic juggling pattern. This is called a 3-ball cascade. Okay, and remember this as the foundations of 3-ball juggling, because we're going to return to this idea later. 3-ball juggling pattern called the cascade. Now, we can add a 4th ball, and I'll show you the fundamental 4-ball juggling pattern called a 4-ball fountain. All right, and we're going to come back to this idea also. So take note of what the 4-ball fountain looks like. And I got one more for you. The 5-ball cascade. It will look very similar to 3 balls, but it will be a larger and higher thrown pattern and significantly more difficult. Here we go. Yeah? Okay. So now that you've got an idea of what the juggling looks like, let me put it all together with some mathematical ideas. So how do jugglers discuss juggling? Well, as it turns out, things get very complicated very quickly. And so jugglers develop this notation, this mathematical language called site swap. I don't think this is backwards, but it might be. Site swap notation. That's what we're going to talk about today. We're going to talk about the most basic form of site swap notation, which is vanilla site swap. And vanilla site swap is based on 2 main assumptions that we can add in to our juggling patterns here. So again, let me remind you here what a 3-ball juggling pattern basically looks like. Okay, this is called a 3-ball cascade. Each one of these throws, I'm going to label with the number 3. Why? Well, each ball is actually thrown every 3rd beat. Okay, so if you watch, I'll add a big orange juggling ball into this pattern so we can count every time the orange ball is thrown. And I'm going to count, and it's going to be thrown every 3rd throw. So here we go. Let me try. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so as you watch the orange ball go around, you'll notice that it's thrown every 3rd throw. So this pattern we can describe simply by 3, 3, 3. Okay, that's the cascade pattern. 3, 3, 3. Every ball is thrown every 3rd beat. Similarly, if we look at the 4-ball juggling pattern, we can watch the orange ball and count, and you'll notice that it is thrown every 4 beats. Hence, we'll call this 4-ball fountain pattern 4, 4, 4, 4. 1, 2, 3, 1, 2, 1, 2, 1, 2. Okay? And lastly, the 5-ball juggling pattern. Let's count the orange ball and make sure it gets thrown every 5 beats. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So that is the foundations of how we're going to describe juggling patterns. The numbers 3, 4, and 5 relate to the basic 3-ball, 4-ball, and 5-ball juggling patterns. We've left 3 numbers out though, and that's numbers 0, 1, and 2. What do those numbers look like? Well, a 0 looks just like an empty hand. Because imagine I was juggling no juggling balls, I would have 2 empty hands. That's what we'll call a 0. And this is an important concept because of our assumptions that I'm going to mention in just a minute about how this notation works. The number 1 represents how I would juggle one ball as it switches between hands. 1 is going to be a zip from one hand to the other hand, back to the same hand, over and over. Okay, this is a 1, 1, 1, 1, 1 pattern. And the number 2 can simply represent holding something in each hand, not throwing them at all. If I was juggling 2 balls and I have 2 hands, all I need to do is hold them, or I can do something a little fancier if I want. But this is a 2. So now keep that in mind. 0, 1, 2, 3, 4, 5, and we can go higher and higher with numbers. I can only juggle 5 balls at a time though, so we'll stop there. Now, this is the basic idea of juggling site swap. We assign a number to each throw represented by where it would fit in this basis set of the most fundamental juggling patterns with different numbers of objects. But I can combine these different throws together to get more intricate patterns, and I'll show you a few. But we have to discuss 2 main assumptions with this juggling site swap notation. The first assumption is that the ball exchanges, each hand throws objects alternatively. So I throw left, right, left, right, left, right. I always have to throw with my left hand, following my right hand, and so on. Okay, so that's my first assumption. That is not necessary for juggling in general, but for this basic language that we're discussing today, it is. So that is an assumption we must make. I will throw left hand and then right hand. That's why it's important to have zeros for this particular language, because imagine now I'm juggling 2 balls in one hand. I need to account for the fact that this hand is empty the whole time. So this pattern would be called 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0. And so I need that 0 to describe the empty hand. Okay? So that's our first assumption. The second assumption is that we only have one object in any hand at any one time. That is not necessarily true for all juggling patterns, but it is true for all juggling patterns that can be described uniquely by site swap, vanilla site swap notation. So if I were to juggle with 2 balls going from the same hand each time around, this would not be a pattern that I could describe using the language that we're talking about today. Okay. Those are our basic assumptions. Now let me show you 3 mathematical implications of the language that I've just described to you, and 3 main implications. The first is that there is a necessary condition on the numbers describing this juggling pattern. So let me pull you a little closer to the whiteboard and I'll demonstrate here. So let's consider a pattern called 4, 4, 1. I'll try to write it where you can read it here on the board. 4, 4, 1. Okay? This is a necessary condition that all the digits describing this juggling pattern add up to a number that is a multiple of the number of objects we're juggling. Let me say that again. If I add up the digits of 4, 4, 1, that's 4 plus 4 plus 1. That equals 9. If I add those digits together, and I know that I can juggle this pattern with 3 balls because the number 9 is divisible by 3. But this is a necessary condition for a pattern to be true, but not a sufficient one. So you may hear when you talk about math a necessary and sufficient condition. This is necessary, but not sufficient to know that a juggling pattern is possible. So let me juggle 4, 4, 1 so you can see how it looks. Okay, so remember that 4 goes straight up in the air like this, and a 1 zips across straight between my hands. Okay, so I'm going to throw 4, 4, and then a 1, and I'll repeat the pattern and see if you can follow here. 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 1. So you'll notice each 4 is thrown up to the same hand, and each 1 zips right across between the hands. That's another consequence of the assumptions we've made, is that every even number describing a throw returns to the same hand from which it is thrown. Every odd number changes hands. So I'll show you again. Each 4 goes up and down. Each 1 goes straight across. 4, 4, 1, 4, 4, 1, 4, 4, 1. Okay. So 4, 4, 1 is a 3-ball juggling pattern. We could not do 4, 4, 1 with 4 balls because 9 is not divisible by 4. Not an integer anyway. Will not be an integer. So that is our necessary but not sufficient condition for a pattern to be possible in terms of our site swap notation. The second implication of this is that multiple juggling patterns can be described by the exact same set of digits in site swap notation. So, for example, let me show you again the most basic form of juggling, the 3-3-3 Cascade Pattern. Okay, here's your 3-3-3, 3-3-3-3. Now consider this. What if I change the way this pattern looks, and now I juggle this? 3-3-3. Right? 1, 2, 1, 2. Every ball is still getting thrown every third throw, but the pattern looks much different. Let me add the orange ball back in here, so maybe it'll help you count a little bit. Okay. So 1, 1, 1, 2. Okay, and keep following the orange ball here. 1, 2, 1, 2, 1, 2. Same site swap notation, different pattern. Now you might think these patterns look alike, and they are. But I'll show you an even more bizarre one that looks much different. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Notice the orange ball is still being thrown every third throw, but I'm doing some wacky, crazy stuff with crisscrossing arms. Okay, so this is what I would call a degeneracy in the notation. So 3-3-3 is many-fold degenerate. There are many different patterns that can be described simply by 3-3-3 that are very distinct in terms of the body's orientation and how the balls are being thrown relative to your body. So there's degeneracy in these patterns. So that's the second thing that's notable about this notation, the consequences of this notation. The third thing is the symmetry in the pattern. Okay, so let's consider 4-4-1 again and look at how many digits there are in the pattern. Here there are 3 digits that are used to describe the pattern, 4-4-1. This implies, since there are an odd number of digits describing the pattern, that this pattern will be symmetrical. The first throw of the first round of this pattern will start with my right hand. 2, 3. The first throw of the second rotation of this pattern will start with my left hand. Therefore, the pattern will go back and forth from being a right-handed pattern to a left-handed pattern, and there will be symmetry in the pattern. So follow the orange ball again and see how it starts on the right side and does the exact same thing on the left side alternatively. 4-4-1, 4-4-1, 1. And notice how the orange ball spends an identical amount of time on the left as it does on the right. You'll also notice that this pattern the 4-4-1 pattern does not return back to its original state for several cycles. So for example, 1, 2, 3, 4, 5. It takes 4 cycles before the orange ball is thrown in the same way by the same hand on the same digit, the first 4 on the 4-4-1 digit. Okay, so the period of the pattern repeats itself every 4 cycles, and it's a symmetric pattern because there are an odd number of digits describing the pattern. I will show you one more thing before I pass us along to see some really great geometric unicycle creations. I will show you an even more difficult pattern that will demonstrate a little more about what we're talking about here. So this pattern is called 6-4-5-1. 6-4-5-1. So think about the sum of the digits. 6 plus 4 is 10, plus 5 is 15, plus 1 is 16. This is a sum of 16. That's going to tell me that I need 4 balls to juggle this pattern. And since it's an even number of digits, I know this is an asymmetric pattern. So it's always going to be right-handed. So here we go. I'm going to give it a good shot. 4, 4, 4, and I'm going to throw in a 6, 4, 5, 1, 6, 4, 5, 1, 4, 4, 4, 4. Did you catch that? That was pretty good. I didn't mess it up that time. Watch one more time. Here you go. This is just your basic 4, 4, 4, and then 6, 4, 5, 1, 6, 4, 5, 1. Notice that the very high 6 throw always came from my left hand. But if I add another digit, the number 4, at the end of 6, 4, 5, 1, 6, 4, 5, 1, 4, I have a sum of 20, still possible with 4 balls, it turns out. But now it has 5 digits describing the pattern, and therefore it's a symmetric pattern. So let me give this a shot to close up my part of the show here. Here we go. 4-ball base pattern, and then 6, 4, 5, 1, 4, 6, 4, 5, 1, 4. Woo! That's a toughie, I'll tell you. Okay. So if you're as good at juggling as I am, that's how you know you spent far, far too much time learning how to juggle. So don't be like me, stay in school. And with that inspiring message, I will take questions after Josh does his unicycle geometry, amazing weird shaped wheels.
Thank you, John. Let's move it over to Josh.
Hello, Mathapaloozans. This is your friendly science clown, Lenny Euler, and I'm here to tell you how circus math can help you think outside the circle. Ha! You probably thought that I was going to say think outside the box. But sometimes, if you want to be original and everybody is expecting circles, you just might want to think inside the box. Take wheels, for instance. Here's a picture I saw in some highbrow magazine where the caption talks about, quote, square wheels and other absurdities. I bet most of you agree that you don't want your wheels to be flat on even one side, much less on 4 sides, because the ride would be very bumpy and it would be difficult to get around. Well, Mathapaloozans, it all depends on the road. Now let's talk about Texas, where they haven't paid much attention to infrastructure lately, and they have some really funky roads out there. But the last time I visited, I had a perfectly smooth ride cycling on one of those funky roads, and it was caught on video. Take a look.
Yes. All you want to do is just stay on the yes. I don't want to go the way, but at the same time, yes.
You see, if you start with some kind of funky wheel that's not a circle, we might be able to use geometry to figure out a special funky road on which it will roll without bumps. And to show you how that happens, I've invited my 2 assistants, Sophie Germain and Danny Bernoulli. Sophie, do you have a car there with some interesting wheels? Can you show it to the Mathapaloozans out there? See? Those wheels are not round. Let's see how well it rolls. Can you try to roll it on this flat surface? Is that rolling very nicely?
No, it's a bumpy ride.
It sure is. I wonder if we could get a mathematician to figure out the special road on which it runs smoothly. Danny, do you think you can design us a road on which Sophie's car will run smoothly?
Oh, here's one that I designed.
Well, look at that wonderful road. Sophie, can you try the car on this special funky road? Does it run smoothly?
Yeah.
What about this one? Would this one roll nicely on that funky road, or does it need its own funky road?
Its own funky road.
Looks like it doesn't roll so good.
Mathapaloozans, maybe you can think about the math that it would take to design the right funky road for that other car. And next time, when you can be there in person, you can play with these cars yourselves. Okay, rolling right along then. As we all know, if you have a flat object, it can roll pretty smoothly on a pair of circles. let's watch. So if you take a pair of circular, Magritte, these are not tori. This is not a torus. This is a right circular cylinder, circular in profile. If we take a flat object, it can roll on a pair of circles very nicely. But is that the only possibility? Ladies and gentlemen and children and anyone else who might be out there, let me introduce you to the Rouleaux triangle. Now the Rouleaux triangle is just like your garden variety triangle, except instead of straight sides, it has circular arcs. And that means it's the same distance across, no matter how you turn it. So if you take one of these shapes, where the width is the same, constant width, you can roll on it just as nicely as on a circle, back and forth, no bumping. Now, let me introduce you to some other interesting shapes. These little babies are three-dimensional shapes of constant width, which means that a flat object will roll on them just as well as on ball bearings. Back and forth, no bumps. So, suppose you went to your neighborhood unicycle inventors club and told them about interesting ways to roll, not just circular shapes. Well, that is just what we did.
Hi, my name is Josh, and I believe unicycles can change the world. I ride for fun. I don't own a car, so when I need to get around town, I hop on my unicycle and go. Whether it's hanging out with friends, advocating for safe streets,
Safe streets for all! Safe streets for all!
exploring new terrains, or taking little used roads, my unicycle is with me. Sometimes I fall off. One day, while hanging out with the local unicycle gang, I met a science clown, Lenny Euler. You may have heard of him. He asked me, "How round is your wheel?" I answered, "Quite round. My spokes are tensioned, my rim is brand new, and my tire has air in it. It's as good as a wheel as you'll get." He looked at my unicycle and asked, "Well, why choose a circle?" "What else would I choose?" I answered. "Anything but a circle would produce a bumpy ride." "Aha!" he countered somewhat triumphantly. "I bet you could build a unicycle with a non-circular wheel that would still produce a smooth ride." You see, we typically think circles make the best wheels because, as everyone knows, a circle has a constant radius. This means you can draw a line from its center to a point on its circumference, and no matter how you rotate this line, the length of the line will remain the same. Alternatively, you can draw a line that goes from one side of the circle to the other, passing through the center point. This is the circle's diameter, or width. Again, no matter how you turn this line, the length of the line stays the same. This condition of constant width is one of the reasons we make wheels round. No matter how you turn the wheel, the distance between the top of the wheel and the ground remains constant. To my great surprise, Mr. Lenny Euler showed me that circles are not the only shape of constant width. That blew my mind. Let me show you how it's done. First, draw a circle with some radius r. Then draw another circle of the same radius, or same diameter, whose center point lies somewhere along the circumference of the first circle. Because both our circles have the same diameter, the center of the first circle will likewise lie on the circumference of the second. Lastly, draw a third circle whose circumference passes through the center points of the first two. Note that the circumferences of the first two circles pass through the third circle's center point. Let's highlight the area formed by the intersection of these three circles. This area has the shape of a rounded triangle where each side is a circular arc. Now for the punchline. If we draw a line from any one corner of the triangle to the opposing arc, we find that this line has a length of r, the radius of our original circles. What's more, this distance does not change no matter how you rotate the line within the rounded triangle. What this means is that, like a run-of-the-mill circle, our rounded triangle, called a Rouleaux triangle, is also a shape of constant width. Don't believe me? Let me show you. Here I have two bars and two of our Rouleaux triangles that I will use as rollers. If their width changed as they roll, we'd see the bars move up and down in a bumpy fashion, but they don't. Look how smoothly the bars glide over our Rouleaux rollers. But enough theory. What science clown Lenny Euler really wanted to know was, can we build a unicycle not with circular wheels, but with Rouleaux triangle wheels? Could this work? So I poked around the scientific literature, the clown literature of course, such as the Journal of Circus Arts, the Proceedings of the National Academy of Unicyclists, to see if anyone had thought about a unicycle with Rouleaux triangular wheels before. I eventually came across this paper called The Dance of the Shapes of Constant Width. The paper talks about a ton of interesting things you can do with Rouleaux triangles. Then, lo and behold, on page 16, the author describes the design for a Rouleaux-wheeled unicycle. This design uses a three-wheeler unicycle. Here the rider drives the topmost wheel, and this motion is transferred to the bottom wheel through friction. I decided to take this design and simplify it a bit. Rather than have three Rouleaux triangle wheels, I will only have one. The others will remain circles. I drew my Rouleaux wheel using a CAD program, and then decided to make the wheels out of aluminum. To cut these wheels out, I'm going to use a specialized tool called a water jet. I could explain what a water jet is, however I think my friend Julian can do a much better job. The water jet, what can it do?
Well, we've got a 60,000 psi water jet. Basically what it does is it mixes garnet with water,
Yeah.
has high pressure and fuses through materials, metals, steels, plastics, whatever you want. So we can cut upwards of 6 inches of material.
6 inches of steel?
6 inches of steel.
Oh man.
Exactly.
Let's go check it out.
Sure.
Check it out, folks. We've cut out our Rouleaux triangles using the water jet. So now it's time to turn these profiles into wheels that we can mount onto our unicycle. For that, we're going to go use a machine shop. So let's go cut some metal. was a lot of machine. But I think we are done. So here we have our Rouleaux triangle wheel. Got the nice bearings on which it will roll. We've rubberized the edge here so we can get some friction with the ground. So the last thing we need to do is mount this on our regular three-wheeler unicycle. And for that, we're gonna go pay a visit to the bike co-op on campus. So I'll see you there. So here it is, folks. We're back in the shop, and we've completed the Rouleaux Triangle three-wheeler unicycle. So a disclaimer, I unfortunately do not know how to ride this yet. So what that means is that you'll have to come back to Mathapalooza next year to see me ride it. But in the meantime, we can test whether this design works in principle. So as we mentioned, a Rouleaux triangle is a shape of constant width. So if I were to push this unicycle along like this, and then look at the saddle, we should see the saddle stay at a constant distance from the ground if this is working properly. So this is a bit of a cramped space. Why don't we go back outside and we can test whether that works. So thanks everybody for watching. I hope you enjoyed this video as much as I enjoyed making it. I'm hoping I'll see you next time for Mathapalooza next year when I will be riding the unicycle, and hopefully that time it'll be in person. Cheers. Coffee time.